Hi again, 3U and 4C chemistry students. Today we're going to combine what you learned in the last lesson about titration, the laboratory procedure, with stoichiometry. So it's kind of a combination review lesson. So titration is a lab procedure where we use a piece of equipment called a burette, and we are able to determine the concentration of an unknown solution. The way we do that is we have to use a predetermined volume of our unknown solution, must be very accurately measured. And then in a burette, we put what we call the titrant. And the titrant has to have a known concentration. Then we add the titrant with the known concentration to the mystery solution. But prior to doing that, we must put an indicator in that'll change color, and that's going to tell us when our mystery solution has changed from either a base to an acid or an acid to a base, and that is when it has become neutral. And the color change is called the end point. Okay, so frequently when we do titrations in labs, and they are done in all sorts of quality analysis, like environmental labs where you're testing water samples, medical labs, food labs in quality assurance. But when we do a titration, we often do it 2 or 3 times to be accurate, and then we get an average of our results, and then we can be quite sure that that is accurate. So the chart that you would record your results from your titration would look something like this. So I have 2 trials for this particular example. And this is a titration that could have been done in a food processing plant. So strangely enough, in a plant, maybe like Campbell's Soup, for example, where they're putting lots and lots of potatoes into their soup, someone does not stand there and peel all those potatoes. The potatoes are actually peeled by sodium hydroxide. So a strong base is that it just literally eats the skin right off the potatoes. Now, the concentration of that base needs to be within a certain range, firstly, to effectively remove the potato skin, but secondly, to be safe in that, once it gets rinsed off, then it is going to be safe to consume those potatoes. So someone needs to be testing the concentration and making sure it's replenished, because it's going to get dilute after time if more fresh potatoes keep being put into it, for example, and then it won't work as well. Okay, so our question is, in a titration to test the concentration of the sodium hydroxide solution used to peel potatoes, a 10 milliliter sample of sodium hydroxide was used, so that would have been accurately measured. And then it ends up getting neutralized by, we're going to find out how much of a 0.13 mole per liter sulfuric acid titrant. So the sulfuric acid is what is going in the burette, and then we add that until we reach the end point. So the burette is calibrated, so if you filled it right to the top, the reading would be 0.0. You don't have to fill it right to the top. You can have any initial reading, but that is, easy. Then after our first trial, it went down to 16.3. So if you take the final volume, subtract the initial, we know that 16.3 milliliters of sulfuric acid was required to neutralize the sodium hydroxide. So now your burette is sitting with the sulfuric acid level at 16.3. So you can use that as your initial volume, repeat the whole process, get a fresh 10 milliliters of sodium hydroxide, and repeat. And this time we get 16.5 mils. Because titration is an art, and stopping adding the titrant at exactly the end point can be difficult. So sometimes you get slightly different results, and that's why more trials is best. So based on this, because we had 2 trials, if we added them up, divided by 2, we would say, okay, we're going to go with 16.4 mils. That is what was required. Okay. Okay. So just for a little bit of review, I did not give you the balanced equation this time because we should be able to figure that out. So sodium hydroxide solution has sulfuric acid added to it, which is H2SO4. And then because we're trying to neutralize, obviously one of our products is going to be water, which you would have learned in our last lesson. And the other product is going to be a salt. So the hydrogen got together with the hydroxide, and the sodium is going to get together with the sulfate. This is a double displacement reaction. So sodium is a +1 charge, sulfate is a -2. So when we crisscross, this is our salt. Okay. So now we're going to do what we always do with stoichiometry, and we're going to write down everything we know under the appropriate column. So the sodium hydroxide, we very carefully took a volume of 10 milliliters to test. We know we can't do calculations with molarity or mole per liter concentration with milliliters, so you are going to convert that. 1,000 mils on the bottom, 1 liter on top. So 10 divided by 1,000, 0.100 liters, if I keep all my significant digits. Okay, now this is what we're interested in the concentration of. Determine the concentration of sodium hydroxide. So there's our question right there. Now, under the sulfuric acid, we have a volume of 16.4 mils, which is equivalent to 0.0164 liters. And we knew the concentration of it, which you have to always know the concentration of your titrant that goes in the burette. Okay, so there's all our known information. Now, at this point, like all stoichiometry, you need to get something into moles. So there is only one thing that we have the information to get to moles, and that is sulfuric acid, because we know its concentration and we know its volume. So just to remind you here, we have a little formula. Concentration is moles divided by volume in the magic triangle. So N is equal to concentration times volume. So 0.13 moles per liter. I'm going to multiply that by 0.0164 liters. Getting very small numbers here. And I believe you get like 2.13 times 10 to the -3 moles, and that is of sulfuric acid. Scroll up here a little bit. Okay, so once you've got moles of something, remember that's your ticket to hop to moles of something else, and that is using our molar ratio. So, big lesson here. Always balance your equation, which I skipped right over. I definitely need a 2 here because there is 2 sodiums, and that is going to give us 2 plus 2, 4 hydrogens. I'm going to need 2 water to get 4 hydrogens. And then we have a sulfate and a sulfate, 2 oxygen. Okay, now we're balanced. There. As long as when you go to use your mole ratio, you notice if you're balanced or not, then you're okay. So on the bottom, 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. Okay, so there's our mole ratio. So we're going to double this. So 4.26 times 10 to the negative 3. But notice moles of acid are now canceled and we have changed our substance. Okay, so this is sodium hydroxide. We can take this up here, and I'll just rewrite it. So 4.26 times 10 to the negative 3 moles. And we wanted the concentration. So now we have the volume already. We've got the moles now. We want concentration. C is N over V. So 4.26 times 10 to the negative 3 moles divided by 0.0100 liters is going to be 0.426 moles per liter, or perhaps you want to write it in scientific notation, which is fine, 4.26. And because I made this bigger, I need to say times 10 to the negative 1 moles per liter sodium hydroxide. And that is our final answer. So for those of you who are have been doing very well at stoichiometry, this will be getting boring and repetitive. But that's okay, because stoichiometry is a big concept that really you should definitely have a good grasp on by the time you're done 4C and 3U chemistry. So I'm okay if you're getting bored. And if you have been having trouble with it, then you're getting more opportunities to get this concept down pat, because it does come up several times during the course, as you have noticed. Okay, so I'm going to give you a few practice questions and then a little assignment. Have a good day.